Hello and welcome to Sustainable and Renewable Energy Sources and Their Utilization FIU online course EEL 5285C and EEL 4930. Today I will introduce you to module 2, and this module actually is divided into two parts, part 1 and part 2. Here we will cover part 1 and later we will cover part 2. The module talks about solar energy, and actually part 1 of it provides a detailed description of solar resource and the basics of solar photovoltaic and its various technologies. In part 2 we will cover the analysis and design of solar PV systems. Then we will provide an introduction to solar thermal. This module is linked to the following course objectives, which is identify the theoretical and practical background associated with designing systems and predicting their performance, and describe the integration challenges with the grid and provide solutions. Okay, now the module objectives. By the end of this module, you should be able to identify and calculate the different solar PV related angles, such as the altitude, azimuth, latitude, tilt, and other angles. Also define the meaning of solar photovoltaic, explain the equivalent circuit of solar PV cell, identify solar PV cells, modules and arrays and the differences between them, explain the effect of changes in temperature, radiation level and shading on the IV characteristics curve of the solar PV cell, identify the different solar PV technologies, design a solar PV system, and at the end identify that get introduced to solar thermal systems. Now let us start with our module, and we start with the outline. As I mentioned, in this part I will cover the solar resource, solar photovoltaic, and the basics of solar photovoltaic actually, and solar PV technologies. The beginning is gonna be with the solar resource, and in order to talk about solar energy and the design of solar systems and the analysis of these systems, first we need to know how much sunlight is available for us in order to produce energy from the sun. Okay, so by that we will start talking about the solar radiation. So as the solar radiation makes its way toward the Earth's surface, some of it is absorbed by various components in the atmosphere, giving the terrestrial spectrum an irregular shape. Now there is a definition called the air mass ratio. It is actually a measure of the amount of atmosphere the sun's rays pass through to reach the Earth's surface. So how much atmosphere the sun's rays pass through in order to reach the Earth's surface. This air mass ratio is abbreviated by M, and it's equal H2 over H1, or 1 over sine beta. What is beta? Beta is the altitude angle of the sun. So this is the first angle that we got introduced to related to solar resources. Okay, so here we have the altitude angle of the sun, and H2 is the length of path taken by the sun's rays as they pass through the atmosphere, and H1 is the minimum possible path. We will see this in the next slide in details. In this slide we can see again the definition of air mass ratio, H2 over H1, where here H1 represents the shortest path and H2 represents the path that the sun rays will follow or take in order to reach the Earth's surface. Okay, and beta here is our altitude angle. Now here we can see that as the air mass ratio increases, So here we have M0, M1 up to M5. That means the sunlight is passing through more atmosphere. So passing through more atmosphere means that less energy arrives at the Earth's surface from the sun, and the spectrum, you can see here, it shifts toward the longer wave, so increasing the value of and also increasing the wavelengths. Now here we can see that the Earth revolves around the Sun in an elliptical orbit. This orbit shown here, this elliptical orbit where the Earth revolves around the Sun, okay, and actually making one revolution every 365.25 days. So the Earth makes one revolution, okay, every 365.25 days, and this is around the Sun, while the Earth rotates around itself 360.99 degrees in 24 hours. Okay, so the first part is when the Earth rotates around the Sun, and here when the Earth rotates around itself, okay, to form the days, and to the morning and night, and to form the seasons. Okay, now the point at which the Earth is nearest the Sun occurs on January the 2nd. Okay, and what is the distance between the Earth and the Sun at this point? It is around 145 million kilometers. Okay, so on January the 2nd we have the shortest distance between the Earth and the Sun, while the longest distance between the Earth and the Sun, it occurs on July the 3rd, and the maximum distance is around 152 million kilometers. Okay, so this is the longest distance and this is the shortest distance. Okay, now this variation in distance is described by this equation here, in which we have n in this equation that represent the day number, with January 1st as day 1 and December 31st as day number 365, representing the last day in the year. Okay, now for solar energy applications, the characteristics of the Earth's orbit are considered to be unchanging, but over long periods of time, measured in thousands of years, orbitical variations are extremely important, as they significantly affect the climate. Now, changes in the orbit affect the amount of the sunlight striking the Earth, as well as the distribution of the sunlight both geographically and seasonally. Okay, that's why it's important to study the Earth's orbit variations for planning purposes or long time purposes. Now in this slide we can see a table that represents the day numbers for the first day of each month. So in January 1st the day number represent 1, and February 1st represent the day number 32, March 1st represent day number 60, and so forth. Now, predicting exactly where the sun is in the sky will be at any time, at any location, on any day of the year helps in designing an overhang, for example, to allow the sun to come through a window to help heat a house in the winter while blocking the sun in the summer. Also, it helps in picking the best tilt angle for solar PV modules to expose them to the greatest insolation. Now the figure that we saw before that showed the Earth rotating around the Sun in elliptical orbit, or the Earth rotating around itself, is actually difficult to use when trying to determine the various solar angles as seen from the surface of the Earth. So here in this figure, in this slide, it shows the solar declination delta here. Okay, this solar declination is the angle between, let me show you. Okay, is the angle between the equator and the Sun. Okay, so solar declination angle between the equator and the Sun, and it actually varies between two extremes, which is the plus 23.45 degrees and minus 23.45 degrees. While a simple sinusoidal relationship that assumes a 365 day in a year, and which puts the spring equinox on day 81. So this represents the spring equinox. Okay, this equation provides a very good approximation for delta, which is again the solar declination. Now in the northern hemisphere, facing a collector as shown here, toward the equator means facing it south, in south direction, like shown here. This is the south direction, and tilting it up with an angle equal to the local latitude. So L is the local latitude, okay, that is used to tilt our collector from the south position. Okay, this way is actually a good rule of thumb for providing a good annual performance for our solar collector. Okay, so L, just a reminder, represent the local latitude. Okay, and actually this is the way that we facing the collector toward south. Okay, and this is in the northern hemisphere. Now, as can be seen in the figure, that in like for winter collection, we might want to increase the latitude angle, and for summer efficiency, we might want to decrease this angle in order to increase the collection or the efficiency of our solar collector. And now there is something called the zenith. This zenith is actually axis drawn directly overhead at the site. Okay, so it's the overhead at a site, axis overhead at the site. Okay, so based on that, our altitude angle that we talked about before when we talked about the air mass ratio equals to 90 degrees minus the latitude plus delta, which we described before as the declination. And the figure here shows clearly the differences between the altitude, the declination, the angle between the equator and the sun, and the latitude. Okay, and the latitude again here. Now let us solve an example to apply the concept that we have learned in the previous slides. This example is asking us to find the optimum tilt angle, okay, for a south-facing photovoltaic module, means in the northern hemisphere, in Tucson, which a city in Arizona that has a latitude of 32.1 degrees at a solar noon on March 1st. Now to start the solution of our problem, we need first to find delta, which is our declination. Okay, now using the equation that we mentioned before to calculate the delta, we need to find first n. N for March 1st is actually the 60, day number 60 in a year. That's why we substituted here 60, and based on that we get that the solar declination is minus 8.3 degrees. Now we use the solar declination and the latitude given in the example in order to calculate to calculate beta, which is our altitude. Okay, now beta, based on the equation also we mentioned before, is 90 minus the latitude plus the declination. 90 minus latitude is 32.1 given in the example, and the calculated declination, which is minus 8.3. This will give us 49.6 degrees as our altitude. Now altitude that we calculated is not the tilt angle. The tilt angle is going to be 90 minus the altitude, which is shown in this figure. Here this part is the tilt angle of our photovoltaic module. Okay, so 90 minus the 49.6 will give us 40.4 degrees as the optimum tilt angle for the solar PV module in this place. Now the sun's position can be described by its altitude angle, which we defined before as beta, and its azimuth angle, which is phi s. This is a new angle that we are adding to the previous angle that we mentioned before. Now the azimuth angle and altitude angle of the sun depend on the latitude, day number, and most importantly the time of the day. For now we will express the time as the number of hours before or after the solar noon. Just before we continue on this topic, I will show you that here is the azimuth angle that I mentioned. Okay, and we will see later how we will calculate it. Now for example, for the time of the day, if we said 11 a.m. in solar time, 11 a.m. in solar time is 1 hour before the sun crosses your local meridian due south for most of us. Now the equations shown below the figure here, sine beta and sine phi s, are used to calculate the altitude and the azimuth angle. I know that before we found an equation for the altitude, but that equation did not include the time of the day. So this is kind of modified equation that included the time of the day for the solar time. And the second equation, as I mentioned, is to calculate the azimuth angle. Now the h here represent the hour angle, which is the number of degrees that the earth must rotate before the sun will be directly over your local meridian. So the number of degrees the earth must rotate before the sun is over your local meridian. This gives you the h, which is the hour angle. So let me write here, h is the hour, okay, it's already written, angle. Okay, so the hour angle can be calculated using this equation, which is 15 degrees divided by hour multiplied by the hours before the solar noon. So the difference between the local meridian and the sun's meridian is actually represented by the hour angle, with positive values occurring in the morning before the sun crosses the local meridian. Then after that the values will be negative. So if we assume that this is here the local meridian and this is the sun meridian, so okay, sorry, let me erase this. Okay, and this is the sun meridian, so the difference between them represent the hour angle. We will see how to use that in the next slide when we solve an example. Now let us solve an example about the previous slide that we talked about. Okay, so here in the example is asking us to find the altitude angle, so we need to find beta and the azimuth angle, which is phi, for the sun at 3 p.m. solar time in Boulder, Colorado. Boulder, Colorado has a latitude of 40 degrees on the summer solstice. Okay, now so here is summer solstice. So how to solve this example? First, in order to calculate the altitude and the azimuth, we need what? We need the hour angle. The hour angle, based on the equation that we learned before, is 15 degree over hour times the hours before the solar noon. We said the hours before the solar noon is gonna be positive, and after that it's gonna be negative. Since we are talking about the 3 p.m., that means it's 3 hours after the solar noon. That's why it's minus 3 hours, and based on that we will get minus 45 degrees. Okay, so this is our hour angle. We substitute this angle in the formula that we use to calculate the altitude, and here this the latitude value and the latitude value. What is that? 23.45 degrees. It is the summer solstice. Since we know it's at the summer solstice, that means it's 23.45 degrees our declination value. Okay, now based on that we get that sine beta, or sine the altitude, is equal to 0.75. Then we take the sine inverse to find the altitude angle, which is 48.8 degrees. Now what about the azimuth? The azimuth, we use the formula again to calculate the azimuth angle, and by using it we will find this value. Then we take the sine inverse in order to find the azimuth. Now the sine inverse will give us minus 80 degrees, and also we have another option, which is 180 minus the sine inverse value, which will give us 260 degrees. So which one to choose? We need to use the test that we talked about, the hour angle test. First we take the cosine of the hour angle, which is cosine the minus 45, which will give us 0.707. Then we take that tan for delta over tan L, which is tan at 23.45 degrees over tan 40, and this will give me 0.517. Now if the cosine H is greater than or equal to tan delta over tan L, that means the azimuth angle is gonna be the magnitude, or the absolute value of the azimuth angle, is gonna be less than or equal to 90 degrees. And this is the case. We can see that the cosine H is greater than tan delta over tan L, so our solution for the azimuth angle is gonna be minus 80 degrees. Okay. Now, in addition to the sun path diagrams, predicting the shading patterns at a site is very important consideration for photovoltaics, which are very shadow sensitive. So the figure here shows a sketch of the azimuth and the altitude angles, okay, for trees, buildings, and you can also add other obstructions if you want along the southerly horizon that can be drawn on top of the sun path diagram. Now, the sections of the sun path diagram that are covered by the obstructions here indicate periods of the time when the sun will be behind the obstruction and the side will be shaded. This is hourly watt per meter square and daily kilowatt hour per meter square in a day. As shown here, so this is kilowatt hour. Slides. So we will now solar flux that strikes the collector will be a combination of direct beam radiation that passes in a straight line through the atmosphere to the receiver, and diffuse radiation that has been scattered by molecules in the atmosphere, and the final thing is the reflected radiation that has bounced off the ground or other surface in front of the collector as shown in this figure. So we have here the direct beam radiation, we have here the diffuse radiation, and we have here the reflected radiation. Now the solar collectors that focus the sunlight usually operate on just the beam portion of the incoming radiation, since those rays are the only ones that arrive from a consistent direction. Most of photovoltaic systems do not use the focusing devices, so all three components, the beam, the diffuse and the reflected, can contribute to energy collected in solar PV. The equations in the figure are used to calculate IB, which is the beam portion of the radiation reaching ET, flux, and K is the optical depth. So using this equation you can calculate the optical depth. Let me write down here for you. Optical depth and A is the apparent extra terrestrial. Okay, and here is the beam portion of the radiation. Now, after we learned about the solar resource and the different aspects of the sun and how this energy reaches the Earth's surface, we're gonna talk about solar photovoltaic and know how to use that sun energy in order to produce electricity. Photovoltaic actually is a material or device that's capable of converting the energy contained in the photons of the light into an electrical voltage and current. The photovoltaics use semiconductor materials to convert the sunlight into electricity. Now, if you want to know about the solar PV physics and more information about that semiconductor materials, you can watch that YouTube video. I'm not gonna show it here, just go to this link. You can either copy it from the lecture video or from the lecture notes. Then after you watch this video, you will answer the following practice questions. They are ungraded, so they are just to test your knowledge. Then we will continue the next slides. Now, for solar PV, there are two conditions of particular interest for the actual PV and for its equivalent circuit. The first thing is the current that flows. Okay, let me use the pointer. Okay, the current that flows when the terminals are shorted together, which called the I short circuit current, and the voltage across the terminals when the leads are left open, which is V open circuit. So these are two important quantities when we are talking about solar PV equivalent circuit, the I short circuit and the V open circuit. Okay, here we can see the equivalent circuit for a PV cell that includes both parallel and series resistances. This is parallel resistance and this is a series resistance for the cell. Now, for the solar equivalent circuit, we can get these mathematical expressions that describe the circuit and how it operates. The first equation represents the voltage current characteristic curve for the PN junction that you learned about when you watched the YouTube video of Shockley diode. So this describes the PN junction of the diode. And the second equation is the current, which is the I short circuit minus the I diode, and the voltage across the diode is V plus IRS. Then finally, the last equation is the equation that describes the voltage current characteristic curve for the PV equivalent circuit. Okay, so this is for PV equivalent circuit. Now, under the standard assumption, with a 25 degrees Celsius temperature for the cell, we can get this equation for the current passing through the series resistor, and by applying the Kirchhoff current law to the node above the diode in the equivalent circuit figure of the cell, we can get this relation that the I short circuit is I, the current passing through the series resistor, plus I diode plus I parallel, or the current passing through the parallel resistor. Then based on that, the expression that we're going to use to calculate the current that goes into or out of the cell and passes through the series resistor can be shown in this equation. Now, solar PV applications with individual cell produces only around 0.5 volts. Okay, so the basic building block for PV applications is the module, since it consists of a number of pre-wired cells in series, and they are all encased in tough weather resistant packages. A typical module has 36 cells in series and is often designed to generate 12 volts. Even though it's capable of delivering much higher voltages than that, some 12-volt modules have only 33 cells, which can be used as a very simple battery charging systems. Now, large 72 cell modules are now quite common, some of which have all of the cells wired in series, in which case they are referred to as 24-volt modules. Some of the 72 cell modules can be field wired to act either as 24 modules with 72 cells in series, or as 12-volt modules with two parallel strings having 36 series cells in each. Multiple modules can be wired in series to increase the voltage, or in parallel to increase the current. Now, an important element in PV system design is deciding how many modules should be connected in series and or in parallel to deliver whatever energy is needed. Such combinations of modules are referred to arrays. So we have the cell, we have the module, combination of cells, then we have array, which is a combination of modules. This figure clarifies the idea that I talked about. We have the cell, the module has multiple cells, and the array has multiple modules. Now, to find the voltage across an individual cell, we refer to the equivalent circuit for the solar PV cell that we talked about before. You can find this that it's VD, the voltage across the diode, minus the current multiplied by the series resistance, and across the module it is N times the VD minus IRS, or N multiplied by the voltage across an individual cell. This N represents the number of cells in a module. Now let us solve an example that contains the cell and module concept. Here in the example, it says that we have a PV module that has 36 identical cells, and they are all wired in series. So the purpose is to increase the voltage with an insulation of 1 kilowatt per meter square. Each cell has a short circuit current of 3.4 amps, and it's at 25 degrees Celsius, and with the I naught equals to 6 times 10 to the power minus 10, which is the reverse saturation current. Now the parallel resistance of this of the cell is 6.6 ohm and the series resistance is 0.005. They're asking us to find the voltage, the current and the power delivered when the junction voltage of each cell is 0.5 volts. So in order to start solving the question, we need to find the current of the cell. The current is gonna be I short circuit minus I D minus VD over RP. Okay. Now this is from the relation that we found before, we talked about in the previous slides. Now VD here is 0.5 given in the question, and same here, the RP also given in question 6.6, and I know the reverse saturation current is 6 times 10 to the minus 10, and I short circuit was given to be 3.4 amps. So all the required information are there. By that we can calculate the current, which is 3.16 amp, the current passing through one cell and all the cells, since the module cells are connected in series. Now what about the voltage of the module? The voltage of the module is the summation of the voltage of each cell. Okay, the voltage of each cell is the V diode minus IRS. VD is 0.5 and IRS is 3.16 times 0.005. This 3.16 is the current that we calculated in the previous slide, and they are all times 36, the number of the cells that we have. This will give you the voltage across the module. What about the power? The power is the voltage in the module multiplied by the current. The current is the 3.16 and the voltage we just calculated 17.43 volts, which will give you 55 watts. Now for modules connected in series, so here the modules are connected in series. The IV curves shown here. Okay, current voltage curve are simply added along the voltage axis. So this is the curve for module 1, this is the curve for module 2, and this is the curve for module 3. That is, at any given current which flows through each of the module, the total voltage is just the sum of individual module voltages. Okay, so here we have group of modules, means this is considered as array. So the sum of the voltages to get the voltage of the array, and we have the same current in all the array because modules are connected in series. Now for modules connected in parallel, so here the modules are connected in parallel. The same voltage is across the module since they are in parallel. So here we have the same voltage, and the total current is the sum of the currents, and this is at any given voltage. The IV curve of the parallel combination is just the sum of individual module currents, as can be seen here at that voltage. Now when high power is needed, the array will usually consist of a combination of series and parallel modules, for which the total IV curve is the sum of individual module IV curves. Now there are two ways to imagine wiring a series parallel combination of modules. The first one is shown in figure A, where we have here the series modules may be wired as strings, and the strings are wired in parallel. The other way is that the parallel modules, as shown here, may be wired together first, and those modules combined in series as shown in figure B. However, to prefer the wiring of strings in parallel in figure A, yes, we prefer that, because if an entire string is removed from the service for some reason, the array can deliver whatever voltage is needed by the load, okay, because they are wired in parallel, although the current is diminished, which is not the case when a parallel group of modules is removed, like in figure B. Now this figure shows a generic IV curve for a PV module that identifies several key parameters to describe the solar PV, such as the V open circuit and the I short circuit, and the product of the voltage and current, that is the power delivered, shown by this curve, by the module. Now at the two ends of the IV curve, at this end and at this end, okay, the output power is 0, since either the current or the voltage is 0 at those points. Now the maximum power point is a very important concept related to solar PV, is actually the spot here near the knee of the IV curve, at which the product of the current and voltage reaches the maximum value. Okay, so here we have at this point we have the maximum VI product. Okay, now the voltage and current at the maximum power point are sometimes designed to be called the VRIR or VMIM. So here we have VR, IR, or VM, IM. Now there is another quantity that we can use to describe or characterize the PV module, which is called the fill factor, as shown here. This fill factor is the power at the maximum power point divided by V open circuit times I short circuit. So it's VRRI over V open circuit times I short circuit. Okay, it seems that there is something wrong with this slide. It's okay, I will explain it. Now PV curves shift all around as the amount of insolation, the temperature, and shading of the cell varies. So there are three things that affect the solar PV curve. Okay, insolation, temperature, and shading. The standard test conditions, the STC, have been established to enable fair comparisons of one module to another. Okay, those test conditions include the solar irradiance of 1 kilowatt per meter square, air mass ratio of 1.5, and 25 degrees Celsius cell temperature with no ambient air. Okay, so all of these parameters are used for the test conditions that are used to establish fair comparison between the modules. Okay, now the key parameter for a module is its rated power, to help remember that it's DC power measured under standard test conditions. Now the current voltage characteristic curves under various cell temperatures and irradiance levels for one type of PV module mentioned here. Okay, it's shown in this figure. So the figure shows insulation drops and short circuit the current drops in direct portion. Cutting insulation in half, for example, drops the I short circuit by half, which is seen here. So as we cut the insulation by half, it will, as we cut the insulation by half, this will cause what? This will cause the I short circuit to drop by half as well, which is the y-axis. Now decreasing the insulation reduces also the V open circuit So as we decrease, we started with this value, then we are moving to the left hand side slightly, since it follows a logarithmic relationship. So the I short circuit gets affected more by the decrease in insulation than the V open circuit, since the V open circuit has a logarithmic relationship. Now the cell temperature increases, the open circuit voltage decreases substantially, as can be shown here, while the short circuit current increases only slightly, that as shown in the figure. Now photovoltaics perhaps surprisingly perform better on cold, clear days than hot ones, okay, due to the temperature effect. For crystalline silicon type of solar cells, which we will talk more about them later in this module, the V open circuit drops by about 0.37% for each degree Celsius increase in the temperature, and I short circuit increases by approximately 0.05%. Now the net result when the cells heat up is that the maximum power point slides slightly upward and toward the left, with a decrease in the maximum power available of about 0.5% per degree Celsius. Okay, sorry for the confusion in the slides, but this slide talks about that the cells vary in temperature because of the ambient temperatures and the insulation on the cells changes. Since only a small fraction of the insulation hitting a module is converted to electricity and carried away, most of that incident energy is absorbed and converted to heat. There is the NOCT, or we can call it as NOCT, okay, which is an indicator that helps system designers account for the changes in the cell performance. NOCT is the cell temperature when the ambient is 20 degrees Celsius, the solar radiation is 0.8 kilowatt per meter square, and the wind speed is 1 meter per second. To account for other ambient conditions, the following expression can be used, as shown here, where S here represent the solar insolation, which is in kilowatt per meter square. Now when the NOCT is not given, there is another approach to estimate the cell temperature, which is based on this equation that uses the insolation and gamma. What is gamma? Gamma actually is the proportionality factor that depends on somewhat on the wind speed and how well ventilized the modules are when they are installed. Typical values for gamma is 25 degrees Celsius and 35 degrees Celsius with one sun insolation, and cell tends to be between 25 to 35 hotter than their environment. Now let us solve example on this. This example is asking us to estimate the cell temperature, okay, shown here. So we need the cell temperature, we need the T cell, we need the open circuit voltage, we need V open circuit, and the minimum output power for, the maximum output power, so we want the P max for one type of PV modules mentioned here, under conditions of one sun insolation and ambient temperature of 30 degrees Celsius. The module has a NOCT of 47 degrees. So since the NOCT is given, we can use the first equation for the cell temperature, and this is the table that has the information about the module that we are working on. Now with the solar radiation of 1 kilowatt per meter square and cell temperature, the cell temperature is estimated using the equation that we learned before, where T ambient is given as 30 degrees, the NOCT given as 47, and this will at the end, and the S is given as 1, it will give you 64 degrees Celsius for the cell temperature. Now based on the table given in the example, for this module at standard temperature of 25 degrees Celsius, Okay, the V open circuit will be 42.8 volts. Since the V open circuit drops by 37% per each degree Celsius, the new V open circuit will be about 36.7 volts, with the maximum power expected to drop by 0.5% per degree Celsius. So for each degree Celsius there is drop of 0.5%. Thus the 150 watt module with its maximum power point will deliver 121 watt. Now adding a bypass diode across each cell will help in solving the shaded cells problem. The bypass diode, when it conducts, it drops about only 0.6 volts. This controls the voltage drop across the shaded cell and limited to 0.6 volt instead of having a large drop that may occur without it. Now to see the effect of bypass diodes on the shading problem, we can see that this figure is drawn for 5 modules, okay, and these modules are connected in series to deliver 65 volts to a battery bank. Now with one module having 2 shaded cells, the charging current drops by almost 1/3 when there are no bypass diodes. But when we add the bypass diodes, there is very little current drop as shown here. So if we go from the 65 volts, the current drop is very little compared when we don't have bypass diodes. Now this figure shows the 5 modules connected together in series that we talked them in the previous figure. We talked about them in the previous figure. Each module delivers 13 volts, and the sum of these voltages will give you the 65 volts required to charge the battery bank. Now the current without any shaded cell delivered to the battery is 3.3 amps. but with the partial shading and without the bypass diode, the current decreased to a significant value, which is 2.2 amps. But with having the bypass diode, the current decreased only to 3.2 amps from 3.3 amps. So without the bypass diodes, a partially shaded module constricts the current delivered to the load. With bypass diode, the current is diverted around the shaded module, as can be seen here. Okay. Now let us talk about another type of diodes called the blocking diodes. These diodes are used when strings of modules are wired in parallel, as shown here. So we have modules connected in series, and this series form a string, and these strings are connected in parallel, one type of the connection that we talked about before. Now this blocking diodes helps also in the shading problem, in this case of connection for the modules. What kind of problem is that? So this problem arises when one of the strings is not performing well. Instead of supplying the current to the array as shown here, so here the current is going to the array, a malfunctioning or shaded string as shown here can withdraw the current from the rest of the array. Now by placing the blocking diodes shown here, they're called also the isolation diodes, at the top of each string as shown here, the reverse current drawn by the shaded string can be prevented. So the current here drawn by the shaded cell is 0, so we will get that the total current is I2 plus I3. But in the case of without blocking diodes, we don't have blocking diodes here, the shaded cell will draw current from the array, and this will decrease the total current by the value of I1. Now after we talked about the modules, the cells and the arrays and the different aspects related to them, we can move on and talk about the solar technologies, what type of technologies we use to build the solar PV systems. One of these technologies is called the crystalline silicon, the other type is the thin film, and the third type is the concentrator. Actually each one of them has different types as well under it. Here we start with the crystalline silicon. The silicon modules, they are shown here in this figure. This is how they look like, and I am sure you saw a lot of them before. Actually the construction of silicon module is simple. We can see here a cross section area for the silicon module. We can see that the glass is in the top, then we can see here the silicon cell and other material under it. They are explained here, but I mean, don't worry about the material part of it. We just want to know general information about these technologies and have a knowledge about them. Okay, so if you hear their name, you know, yes, they are part of the solar PV technologies. This information is taken from Angel, one of the Angel reports. You can refer to it by clicking on this link. Now some information related to crystalline silicon cells, that the silicon part of the solar PV must be fairly thick, and this increased the material cost. That's why we saw, like before 2008 there was like not large production for this type of solar PV, but starting from 2008, when the technology became mature more, we saw a fast growing industries in the crystalline silicon area. Now the advantages of having solar PV built by crystalline silicon material, that It builds on strong industry, and the silicon is an abundant and non-toxic material. The efficiencies of this type of solar PV ranges between 15% to 20%, and this type of technology demonstrated more than 20 years performance in the field, and there is a warranty of less than 1% degradation rate per year, and there is a potential for further cost reduction. What is the disadvantage? The main disadvantage of this technology is that the costs of this technology are higher than the desired one. Now the second PV technology is the thin film, and this shows the three types of the thin film solar PV technologies and how they look like. Now the construction of a thin film solar PV module is different than the crystalline silicon solar PV as shown here, and detailed in this part. Now what are the advantages of using or having a thin film solar PV? One of the advantages is that the material required for thin film solar PV is low or small, and this is reduces the cost. This is actually unlike the crystalline silicon that requires thick silicon material. Another advantage is that we can use a PV plastic wrap, so it comes in plastic wrap shape, and also it comes on spray on paint option, and also it can be integrated into the building facade. Now the disadvantages include that the growth of inexpensive substrates limits the efficiency of this type of solar PV, so its efficiency is lower than the crystalline silicon, and it's sensitive to moisture, and this leads to glass lamination, and the infrastructure is not as well developed as for the silicon. And the last thing is that building integration increases the operating temperature. Now let us move on to the last type of solar PV technologies, which is the concentrator technology, which we will talk more about it when we talk about the solar thermal in part 2 of this module. This kind of technology is mature for almost more than 100 years ago. Now the advantages of such a technology is that it's cheap compared to the crystalline silicon, and its efficiency is really high. It can reach approximately 30%, and yeah, so I think this is the most like two advantages of this type of technology. Now the disadvantage is that it only uses the direct beam, so there is no output on the cloudy days, and it's not yet well established, and it's difficult to integrate into the buildings. Now the companies are looking more now to invest on the concentrated solar PV technologies. They are actually, some of them, setting an automated production lines, and this company are likely to install more than 1 megawatt and this was in 2010, and in Colorado there is a 30 megawatt project of the concentrator solar PV, and it's not clear whether the applications will be limited to utility scale or we can move it to the small residential scale. By that we reached to our conclusion, in which we identified and calculated the different solar PV related angles, such as the altitude, the azimuth, the latitude, the tilt, and etc. Then we defined what do we mean by solar photovoltaic, and what are the equivalent circuits for solar PV. Then we identified the differences between cells, modules, and arrays, and how the modules can be connected together Then we explain the effect of changes in the temperature, irradiation level, and shading on the IV characteristics curve of the solar PV cell. Then at the end we identify the different types of solar PV technologies. By that we reach to the end of our part 1 of this module. Part 2, as I mentioned, will talk about the solar PV system design and will provide an introduction to solar thermal. Thank you so much for listening and watching. I hope it provided you with good information about solar PV. And just to remind you again that our homework 1 due will be on September, let me check. Okay, September 17. Okay, this is the due of our homework 1, and it will be about module 2. Okay, thank you so much, and good luck for the rest of your modules.